Shall we start? Uh, can you hear me, Shulagna?
Yes, sir. I can hear
Yeah, I can hear you. Yes.
you.
Okay, so since we are not going to do anything new today, Shulagna, if you have any further questions regarding uh, your project or the course as such, please go ahead.
Hello?
Yes.
Uh, yeah, sir. So, we have progressed a bit. I mean, as we communicated the last time, we have progressed a little bit. We have built a descriptor that can capture the electronegativity group number, etc. Yes, so hopefully we will be able to show the results to you on Friday.
Okay.
So, sir, I have to like say that, and uh, so
Yeah. Do you have any other question about any other part of the course, any other topic?
um, sir, I up to what I have gone through the old lecture videos, and so there are no more questions like as for now. But sir, for the examination, will there be questions from the graphical neural networks or those parts?
No.
No. In case
Okay,
there
sir.
is something slips, it will be very super easy conceptual. In case anything slips, but I don't think we have. Yeah.
So it will
For
be
example,
most.
question can be as
Yeah.
easy as what kind of input does a graph neural network expects? You will just answer graphs. I'm just giving an example. It should be that easy in case something slips. Yeah.
Oh, okay, sir. Okay, sir. So, so far now, I do not have any problem. So I have gone through the old lecture videos, but yes, I'm able to understand them.
Okay. Yeah, we have the session on Friday also, but even now or Friday, whenever you want, if you want to give any feedback about how, if you would like or would have liked us to conduct, particularly the hands-on sessions in a different manner, or something could have been different, you can tell us.
Okay, sir. Uh, Sir, one thing that I remember is regarding the descriptors like MBTR or ACSF. Sir, you described them quite vividly in the class. But I have, I sir, can you just give the idea of the ACSF in brief? I mean, it was difficult to understand for me.
Okay, let me see if I can bring up that slide. That will make it easier. Just give me a minute or so. Can you see my slide now?
I can see. Yeah.
Okay.
Yes, sir, I can see.
Yeah, so basically these are the two body and three body functions that I had talked about. This is the way this feature has been defined. So you really have to, so if you want to appreciate what this captures, you really have to look at each of these sort of components of ACSF separately and try to understand these. So overall, first of all, there is a cutoff function. And I had shown you a plot of the cutoff function. I'll show it once again. This is the cutoff function, the top left figure. And here
Yes, sir.
it is plotted as a function of R over RC. So whenever R is equal to, so it is 1 when R is 0 and it goes to 0 when R is equal to RC. So anything beyond RC, any distance beyond RC. So if your central atom is at 0, so that's the idea. Atom centered symmetry function. You take one of the atoms at the center and then construct quantities depending on arrangement of the other atoms around it. So any atom that is more than RC distance from the central atom does not contribute. And as the distance increases, the contribution overall is damped out according to this cosine function. Okay, so that is the first thing, that is the cutoff function. After you have defined the cutoff function, then there are three different two-body functions that are defined. So you have one central atom that is at R equal to 0. Then the first two-body function just adds whatever the cutoff value of the cutoff function is. And you have one such component for each atom with atomic number Z1. So for example, I can have a certain transition metal at my center, just to give an example. And then I can have various different atoms surrounding it. So for each atom type defined by the atomic number Z1, I construct one G1. And that G1 is simply the sum over contributions from all such pairs. Okay, and the contribution is just Fc, the cutoff function, when the interatomic distance is Rij. Okay, similarly, you can construct a quantity G2, and which is slightly different from G1. So it has a cutoff, it has this cutoff factor, function factor. So therefore atoms beyond the cutoff radius do not contribute. But apart from that, it has this Gaussian contribution, right? So what that does is, if you can choose RS carefully, this Gaussian contribution will be peaked when Rij is equal to Rs. Now let us go to this, let us look at these plots of the G2 function. For different eta, eta is the sort of damping or the inverse distance of this Gaussian function, which sets the scale, and Rs is a length scale. So eta sort of determines the width of this peak, width of this Gaussian, But apart from that, you see the Gaussians are always peaked around the RA's value. If RA is equal to 2, this blue curve, it is peaked around 2. Not exactly at 2, but it's peaked around somewhere close to 2. This red one is also another plot for R is equal to 2. Similarly, if you have R is equal to 3, those functions are peaked around R equal to 3 or Rij equal to 3. In other words, for different choices of this Rs, you will have large contributions when the distance of a neighboring atom from the central atom is equal to Rs. So now imagine, if you are familiar with molecules or materials, you have say a transition metal complex with a transition metal at the center and the anions around it, maybe in the form of an octahedron or a tetrahedron. These kind of structures occur very routinely in solids and molecules. So if you can put Rs approximately equal to this equal to the distance from the central atom to the anions, you get large contributions. So basically this and if you then construct G2 for various RS values, you pick up these contributions. So you pick up features that capture interatomic distances from the central atom, right? This is a similar function except that you have cosine of Rij. Three body functions are more complicated. You have a radial part and you have an angular part. So it's 1 plus lambda cos theta is the angular part, which basically takes care of the fact that whether these, you have the central atom and then two atoms on two sides, whether the angle between them is 180 degrees or closer to 90 degrees. Based on that, you will get a value for this angular function. And then you have this this radial function e to the minus eta Rij squared, etc., etc. So does that give you some idea? So basically, these are quantitatively capturing information about atomic arrangement of two body motifs and three body motifs, etc. Is that yeah?
Yes, sir. Yes, sir. Right. Then one day you asked a question that if those descriptors are rotationally translated variant. So
Shulaga, your audio was very discontinuous, so at least I could not follow the question.
so descriptor invariant with rotation, permutation, and translation.
Oh, okay. You are asking that question, right? Yeah. So if you look at the functional forms, this is rotationally invariant, right? If you rotate the entire structure, neither the interatomic distances change nor the angles between three atoms would change, right? So all these quantities would be rotationally invariant. They are obviously translationally invariant, again, because angles and distances will not change if you translate the system rigidly. Permutation invariance is not quite relevant here, but or rather another way of answering your question is that yes, it is permutationally invariant, because if you remember this slide, we have already decided to write down or concatenate the various components of G1, G2, G3 in a particular order, irrespective of how the atoms are listed in the structure. So first, I will choose a value of z1 equal to 1, or whatever my first value of z1 is. I will write g1, then I will write all the g2s for different combinations of eta and rs, and then I will write g3 for all values of kappa, etc. Then I'll do the same thing for z1 equal to 2, the second value of z1, then the third value of z1 that I have in my structures. Okay. So I have all, this is a predetermined order. At least this is how things have been implemented in the describe library. So therefore, there is a predetermined order which is independent of how the atoms are listed in the structure of the solid. Okay. So this predetermined order makes it permutationally invariant.
Okay, sir.
All right. So if there are questions, you can ask, or else, Shubhankar, if you have something to say or announce.
No, no. Thanks, Shilagna, for being very
Yes,
regular. Yes,
enthusiastic about it.
yes, yes, yes.
We will have your presentation at usual time, 4:30 on
On
Friday.
Friday.
Sir, it was a pleasure for me to attend this course because I have never, this is first time I am getting exposed to machine learning, and I have learned a lot. If I have not attended this course, then I would not got the opportunity to know this field. And now I am actually writing my thesis. So in fact, I am planning to search postdoc even in this field. So it has been really beneficial for me, this course.
Thank you. We are happy to hear that. But remember that in terms of methods, we have covered a lot, or at least most of the basics that you would need to get started. But the applications part, I mean, things have moved quite far from what we could cover in this course. But if you have a foundation that we try to give with this course, then you can start from there and try to cover up.
Yes, sir. Yes, sir.
Okay, Friday your presentation and Monday exam.
Yeah.
Yeah.
No.
Okay. Bye.
Okay, sir.